So for the Gardner Valley tests, shouldn't the VP below groundwater be limited to VP of water, which is 5,200 feet per second?
No, but the soil could be partially saturated. So because of that, so the Poisson's ratio is close to zero point 0.5, but not exactly zero point 0.5 because it is not water. It is a mixture of water and soil solid, as well as there could be some partially saturated region due to capillary action. I hope that answer your question.
I think so. We will probably get a confirmation from the Zaya soon. Okay, so then we have another question from Maxime to Professor Dearline. So thank you for an impressive presentation. Regarding the PLOM method, how did you decide for an appropriate number of input simulations to use for the PLOM method? And were you able to quantify the epistemic uncertainty resulting from the method due to the limited amount of input simulations? If so, could you propagate these epistemic uncertainties into the performance-based risk calculations?
Okay, yeah, thanks for that question. But I should preface that work that I showed with the plum, that's some just recently completed work, and it actually followed on. I showed two. I showed kind of the first step in the analysis where we did a number of analyses to kind of get those log linear approximations to demand parameters, and then we tried using the plum method and found that it could capture it more robustly, that is capturing correlations between parameters. And frankly, we didn't do, at this point, haven't still trying that out, investigating the answers to the questions you asked. In other words, what's the minimum number of realizations that one would need to train that on? So all I could say at this point is that's kind of a work in progress, but so far it's just been very encouraging. I would point out too that the big benefit of these surrogate models would be that you train them once and then you use them many times. You know, in other words, this could represent, say, one type of building. And I think it's probably true of geophysics and other kind of surrogate models. So the big benefit is not so much in minimizing the training, although that's not, that is important, but it's really doing it robustly so you have confidence to apply these in different situations.
All right, thank you. Okay, another open question from Celine to Professor Dearline again. Very informative presentation, thank you. In the 2018 Alaska earthquake loss study, do the simulated ground motions mean synthetic motions? Synthetic motions or recorded motions selected from historical events?
Yeah,
I hope it was...
yeah, just to clarify that might not have been clear. So when I said simulated motions, they were simulating an observed event, but the way we did that was to basically run a scenario using ground motion prediction equations for the magnitude and location of the earthquake and get target spectra. And then we matched recorded or selected and scaled recorded ground motions to match that target spectra. So that, and by doing so, we could obviously get a much finer grid of ground motions, taking into account the different site classes and so forth throughout the regions. But they were not simulated ones in the sense that we've been talking about the so-called physics-based simulated ground motions.
Okay, great, thank you. And then I would like to reiterate on one question that was just out from Professor Dearline to Norm. And Norm, if you can comment a bit, I know you have posted an answer, but it would be good to share, this with the audience. So Dr. Dearline's question was, most if not all of the validations have focused on comparing earthquake simulations to past events. This is a logical place to start. However, the main promise of physics-based simulations is to explore situations where we don't have data, near fault, large magnitude. What are your thoughts on how to gain confidence in extrapolating simulations to situations where past data is sparse?
Okay, so what I wrote, this is a basic question. How do you validate something where there's no empirical data, right? So we're going to try to validate extrapolations. And the only way that we can really do that right now is to try to find multiple methods, And if they're different enough in their approaches and they're giving us similar extrapolations, then we start to have some confidence in it. But how do you judge extrapolations other than comparing different methods of extrapolating? It's really a tough problem. And as I wrote in there, the problem is all the models could be wrong, right? If they're similar enough in some aspect of them, then they completely miss a behavior. This sort of gets to the same thing that Yusuf was talking about. If you have, you start to get overconfident when your models produce the same thing, even though all the models are wrong. Right. So, and that happens a lot in this business of earthquakes. Yeah. We suddenly realize everything, you know, we all agreed on an approach. This looks right. And then we get data and boom, that model's wrong and we have to start over again. So we don't want to be overconfident. I think we still need to bring along some large uncertainties that may be subjective at this point, but that represent some uncertainty in how the models extrapolate.
Yeah, that I want to add, I think that's, yeah, that's a good answer, Norm. And I think you said it too, maybe comparing models alone isn't necessarily give you confidence, especially if there tends to be groupthink, right? So one thing I think is healthy is that if as a community too, we question the assumptions in models. The benefit, as I see it, of the so-called these physics or mechanics-based models is they're not just purely empirical statistical, right? There's underlying physical phenomenon, and the degree to which we could continue to build that in and have debates on how to best do that. I think that.
So one way we do that in normal seismic hazards when we're trying to characterize uncertainty is we're not looking for best models, which is what science normally does. We try to say, how far can you push this until the data completely are rejecting that kind of a behavior? Mm-hmm. Right. And so I think that's the question you need to ask. How much could I have shoved this in one direction or another in terms of the physical behavior or the distribution of the inputs, and then see what that range is. Mm-hmm. But now you're creating models for which often there's no support, right? Nobody is behind it. And that's one of our difficulties of this.
Great, thank you. And we have one more question from Elnas.
Sure, thank you. Thanks for all great presentation. I learned a lot. So I have a quick question about using multi-fidelity, let's say either surrogate models or even we can think of multi-level finite element models with different types of resolution. So how that can help us with having maybe better adaptive sampling or trying to kind of find our optimal design or goal-oriented, understanding either in propagation of uncertainties or quantifying in parameter estimation.
Sure. Do you want me to take a stab at that? It's a great question. And it's multi-fidelity and multi-level I could think of as a subset of multi-fidelity modeling is a pretty kind of across the board useful tool. Certainly, you can imagine when I talked about some of these, dimension reduction methods, a lot of them involve computing these kinds of matrices that come from gradient evaluations of the model. And you can, and they're essentially expectations. And whenever you see an expectation, you can replace that with a multi-fidelity or a multi-level expectation. And so very useful in that regard. Also, multi-fidelity methods for Bayesian inference are useful too. When people do things like MCMC sampling, you could imagine there's what are called delayed acceptance MCMC methods that essentially say, okay, one of the expensive things in MCMC is you propose a sample and then you go and evaluate your likelihood and you might reject the sample. And in some sense, that's okay, some wasted work. Multi-fidelity or delayed acceptance methods will sort of use a coarse model to pre-screen the sample and then go to the more expensive model and kind of pre-screen it through there. And you can imagine going through a whole hierarchy of models to essentially save the expensive model evaluations only for parameter values that are sort of very plausible. So that's definitely useful there. And I think there's probably, it's a rapidly developing field. There are probably many other ways of using multi-fidelity, multi-level methods in all of this that are still, worth developing and worth thinking about new ways. So, yeah.
And based on your experience, do you think that for the problems that we have in seismology, do you think that that could be a promising approach to kind of test that compared to the existing methods?
I do think so. I mean, so I haven't used multi-fidelity methods in seismology specifically, but in other applications, I mean, you can get multiple orders of magnitude speed up using appropriate multi-fidelity methods. Now, it really depends on having available sort of low fidelity models that are sort of correlated enough with your high fidelity model to be meaningful. And often that's a question of modeling and physics. It's maybe just, coarsening the grid is maybe not enough. Maybe you need to think about other kinds of physical approximations to generate that multi-model hierarchy. And whether that's, available, I don't know, like, acoustic versus elastic wave or ray tracing versus wave pressure. I mean, you could imagine different kinds of physical assumptions to create that model hierarchy.
Great, thank you.
All right, time is up, but if there is any another question from Dave.
Yeah, I was curious, Norm, you talked about this, what I'll characterize as the stochastic engine that Maxine and you've been working on. And it sounds very powerful and useful, particularly if it's non-intrusive and it can be done after the simulation is completed in the analysis code. What sort of time horizon do you see to determining whether that's going to be viable, an application of this problem? Is that 6 months from now? Is that a year from now? It's kind of a important element.
I think it's about a year because of what we need to get. So we need a big enough training set so we can use some of what's there right now. Yep. But then we also need another set that we can use to test, right, the model. So, and a bit of the issue is we need to have the statistics for generating, let's say you're working on source models and you want to have variable source models generated. They need to be following some sort of fixed statistical rule. And right now we have a little judgment put in saying, my stochastic slip model made this, but I don't really like that one. I'm going to throw it out. And that's hard then for any of the statistical models to do.
So the problem is mixing determinism and stochastic characteristics.
Right. Or applying judgment to a stochastic realization and rejecting it is something we have to have some fixed rules.
You would want a fully stochastic generation of the source model in terms of hypocenter and slip and so forth.
So I think it's a year to get to a point where we can go through and say, does this method look like a way we can actually produce time series? So it's a little more than, I think, Greg, you were talking more about scalar quantities, I believe, but I don't know, were you trying to do vectors as well with Plum?
Yeah, we were doing vectors of, we had input as multiple scalars of the ground motion, but the output was multiple response quantities in the structure. So we do have vectors of multiple outputs.
It's a vector, but turning it into a time series. So it's a lot more numbers in the vector, right? But yeah. It's the same idea. And how hard did you find that to apply?
Well, it was amazingly straightforward. I mean, this was one structural model, and I think we had several hundred ground motions in it, and we applied it to that. But I think what we want to do is then explore it for randomness in the structural model, random parameters in it and so forth. But anyway, at first glance, it was very promising. And I think to me, it just opens my eyes to, folks who work in that arena have all these algorithms out there. And if we could just phrase our problems in a consistent way, we could try out different algorithms.
That's key. There's a lot more money in these other fields, right? And we need to take advantage of all that work and try to apply it.
Okay, we have one more question from Arben Pitarka.
Yeah, quick question for Norm. So Norm, you mentioned that we need to consider certain scenarios for the statistics. How many are we talking about for a given magnitude? And can we extrapolate those statistics to other magnitudes or no?
We do. we often will extrapolate into other magnitudes. From our experience in the empirical data, some of the statistics vary as a function of magnitude, so we'll probably have to rely on some of that behavior. This afternoon, I'm going to go a little more into numbers, but if we base this on what we see in the uncertainties in non-ergodic ground motion models, which are our best proxy for the simulations, you're going to need about 30 realizations for a scenario to get 10% accuracy in the mean. Okay, so that's what it all comes down to. And if you want the same sort of accuracy in the standard deviation, you need about double that, about 60. Just given
Okay.
what we've seen in the variation. So it's a big number, right?
Yeah.
And
So Arben,
But it doesn't seem very big though. It is a big number, but not very big.
yeah, but Arben, you're thinking about creating the data set, right? And how
Exactly,
hard
yeah.
it's going to be, right?
Yeah, but 30 is not a
It's a heck
really
of a lot
huge
easier
number.
to create a data set of magnitude 6 instead of magnitude 7, right?
Right, right.
Yeah.
And given the quality of the simulations and the codes, I think 30 to 60 is not a huge number.
Yeah.
It could be achieved.
Yeah, I mean, this was our objective with EQSIM of slapping on a requirement for speed of computation in addition to frequency resolution, is anticipation of something like this.
but then you also have, I mean, that's on the source part, but now we have the uncertainty in the 3D velocity model, right?
Right,
And
that's
these
adding
things all
up.
just start to scale and multiply.
Yeah.
So I think something like these other approximate methods, we just have to try it. And other fields are, showing that it works. So I think need to see if this is going to be a feasible approach for us to build out our simulations without just trying to get more and more computer time.
Although getting more and more computer time can be helpful.
Yep, that's never bad.
All right.
All
Thanks,
right. All right, if you don't have more just pressing questions, this was a great discussion, I think, and I want to thank the speakers again. Oh, we have one last minute question, Elna, so.
Yeah, it's a very quick question. If
Okay.
that I can answer. I just wonder why, what was the issue of not adding the constraint in the time, in the time domain problem to make sure that the Poisson ratio changing between 0 and 0.5? If, you can answer quickly. Otherwise, I can ask him later.
No, it's a good question. No, we did not want to put any constraint over there. We just wanted to check whether the minimum variance framework works without any intervention. And then we looked at all the realizations, means the ensemble average of all the 552 realizations that we generated. And then when we looked at the ensemble average, we saw that everything is kind of mixed up, because you see, you do ensemble average of 10 time series, so you are going to lose the physical characteristics. So that's why we decided to move to frequency domain. Over there, things are not messed up like that when we calculate the ensemble average.
Okay, great. So it wasn't just the physical constraint, basically other things also.
Yes, that's what we realized, yes.
Okay, great. Thank you.